This video is about Gauss-Jordan, or sometimes pronounced Gauss-Jordan elimination on matrices. For our notes, we'll start with the definition, which is that a matrix is in reduced row echelon form when all entries above the leading ones in its row echelon form are also zeros. So you'll notice the familiar phrase row echelon form. We've been working with that lately. This is now going to be what's called a reduced row echelon form. And as you can see in this definition, it's directly related to the row echelon form. Now, using reduced row echelon form to solve a system is called Gauss-Jordan or Gauss-Jordan elimination. Let's try an example which says solve the system using Gauss-Jordan elimination on a matrix with a graphing calculator. You'll notice the request to use a graphing calculator here. Alright, if we can understand row operations well enough to be able to do Gaussian elimination, which we've already done by hand, then we know enough of those operations to get through with Gauss-Jordan elimination, which is simply more work of the same type. So to abbreviate some of that, we're simply going to use the graphing calculator at this point. Now, that will also require us to convert a system into a matrix. And so our first system here is a system of four equations. I'll read through them quickly. The first equation is x minus 3y plus 2z plus w equals negative 2. The second is x minus 2y minus 2w equals negative 10. The third is z plus 5w equals 15. And the fourth is 3x plus 2z plus w equals negative 3. Now, we've already discussed what an augmented matrix is and how to turn a system into one. That's our first step. I'm going to go through each coefficient of each equation and write them in order to create this augmented matrix. So across the top row, we'd have 1, negative 3, positive 2, 1, negative 2. Across the second row, we'd have 1, negative 2. Notice in this case, the z term is missing in that second equation. So we have to fill that in with a 0, as we've seen. Then negative 2, and then negative 10. Going on to our third row, notice the x is missing from that equation, so is the y, which means we have two zeros to start, and then a 1, and then a 5, and then a 15. And lastly, you'll notice the y term is missing. This means our matrix should read 3, 0, 2, 1, negative 3. And that does it for all four equations, now turned into four rows of a matrix. Remember that sometimes you will see authors or textbooks put a vertical dividing bar where you would find the equal signs in each equation. It's not required or necessary to do that, but in case you see that, just know that that's really all that means. It doesn't really do anything different to the matrix itself. Alright, now once we have a matrix from our system, we want to put it in the graphing calculator to utilize its power with Gauss-Jordan elimination. We'll turn on our graphing calculator and then recall that to put a matrix in it, we can hit the second key and then the button that says matrix right above it. And we want to edit one matrix to turn to be the one we've just written here. So I'll just pick on matrix A. Doesn't really matter which one we use. We want to put the size or the order of the matrix. Remember, it's always rows by columns. Well, we have 4 rows in this particular matrix and 5 columns, so this would be a 4 by 5 matrix. Now we'll hit enter and find our way through each entry, plugging them in as we have. Across the top, we have 1, negative 3, 2, 1, negative 2. And then skipping across now the second row, we have 1, negative 2, 0, negative 2, and negative 10. Now, it's a lot of tedious data entry here, and if you make one mistake, it will change everything. So be very careful, double check your work if needed. Our third row is going to be 0, 0, 1, 5, 15. And lastly, Remember now, I'm just hitting each number and then hitting enter every time, and that's how it puts it in the matrix for us. Lastly, we have 3, 0, 2, 1, -3. And that should do it. Now we have matrix A stored with our matrix in it. To utilize the calculator's ability to do Gauss-Jordan elimination, which is also reduced row echelon, we're going to go to the matrix menu by hitting second and then the matrix button again. This time we're going to go over to math, which is the same place we went to find the row echelon form, except this time you'll go down the list and in fact you'll see the REF, that was row echelon form we've used already for just Gaussian elimination. Right below it you'll find RREF, which stands for reduced row echelon form, and so this is the function we want to use to do Gauss-Jordan elimination. So we hit enter. Oop, actually, okay, this can happen sometimes. Be careful, I'm not in the cleared screen yet. This is trying to put what I just typed into the matrix. We don't want that. So let me clear that, and you have to go second quit first, back to the blank screen, then do the matrix operation. So we'll say second matrix, go to math. It's actually faster to go up, and then you'll find it a few from the bottom here, RREF. There we go. We'll hit enter. Now we put our matrix in matrix A, so we'll want to type that in as the input by hitting second matrix and then enter where A is, close parentheses. Now we're going to hit enter and take a quick look at what the result is. Now if you look carefully, you'll observe the exact description that our notes said above, which is it's kind of like Gaussian elimination, or in other words, row echelon form, where you have ones on the main diagonal and then the triangle of zeros beneath those ones. But as we've said, reduced row echelon form now also has the zeros above that diagonal of ones. So as you can imagine, the same row operations could get that done by hand. It's just twice the work sometimes. So that's why we're utilizing a calculator to do this. Okay, so I've simply copied down the result matrix from doing the RREF function on the calculator to our original matrix, and we're going to take a look at what it means. First of all, let's recall that these columns are organized in a very specific way, thanks to the fact that the original system we had was organized with like terms in columns, of course, unless they were missing. So what I mean is, don't notice the first term in each equation was an x term, unless it was missing, which means the first column in our matrix represents the x variable terms, and so on. We have the next column as the y terms, then the z terms, then it was the w terms, and then of course the equal sign and just the constants on the right side. Well, this is really going to help us interpret our result, which is an incredible amount of work done for us. If we could just recall for 1 second what this actually means, let's just pick on the fourth column where the w's were, where this last couple entries of our matrix are. It was just a 1, 3, the last two entries in the last row. What that really means is 1w equals 3, which, yes, is the same thing as w equals 3. It's giving us the direct solution immediately, without any extra solving to do, which we had to do when we used just the row echelon form with Gaussian elimination. But you'll notice if you look through, this is true of every variable in this matrix. Notice every row contains a 1 on the main diagonals, right? That's part of the reduced row echelon form. But then zeros between that 1, actually everywhere else, zeros except for the last column, which is all the constants, which means you can go through one at a time and just pick out the exact solutions. In the third row, where the 1 exists for the z variable, that simply means that z, or call it 1z if you like, equals whatever value it's equal to on the right side in the last column. So in other words, z must be 0. We can kind of work back through and say that y, where the 1 is in the y column, would tell us that y equals whatever the constant is on that side, which is 1. And all the way back in the top left corner, we have 1x equal to -2, which just tells us x equals -2. So from this particular form, reduced row echelon form, you have all solutions, if they exist, immediately without any extra work. which is why this form is very convenient to use. And since I already mentioned, we're going to use a graphing calculator to help with the row operations. It's a very quick way to solve even a large system like we started with. Let's try another example where we want to solve a system using Gauss-Jordan or Jordan elimination on a matrix with a graphing calculator. So again, we're using the technology to help us with all the tedious row operations. We'll want to convert this, of course, to a matrix first, an augmented matrix, and we'll follow with the coefficients from each equation. Now, the first equation reads x minus 2y plus 5z equals 3. Well, if we pull all the coefficients out and put them in a row, that would be 1, negative 2, 5, 3. Our second equation is negative 2x plus 6y minus 11z equals 1, which would tell us our second row is negative 2, 6, negative 11, 1. And our last equation is 3x minus 16y plus 20z equals negative 26. So that means our last row in our matrix is 3, negative 16, 20, negative 26. Okay, so we now have our augmented matrix. Let's take note of the fact that like terms are lined up vertically. We have the x terms, then the y terms, then the z terms, and then all the equation symbols. That has to be the case if we're going to make that assumption with our matrix as well. So let's just note that that is the case. And just to be clear, I'm going to label those variables above each column in the matrix. Now, our goal is to use a graphing calculator to do Gauss-Jordan elimination. So we'll go ahead and put our matrix in and do that next. Alright, I went ahead and typed our augmented matrix into the calculator and then went through the steps to perform the RREF, reduced row echelon form function on it. And as you can see in the screen, it spit out a matrix in that form. Now, you'll notice something interesting. It has the ones on the main diagonal except for this last row. You'll observe that the last row contains only zeros. Okay, having copied down the result matrix, let's again highlight the fact that that last row contains only zeros. Now, with what we were understanding about how to convert a matrix in reduced row echelon form into a solution, this means, technically it means 0x plus 0y plus 0z equals 0, also known as 0 equals 0. Now, that's not the end of the world, but that does mean something very important for us. This is usually what happens when we have a system with infinitely many solutions. In order to come out with our solution, or at least a way to represent all infinite possibilities, as we've been doing, we're going to go ahead and convert our result matrix back into some equations. So if we take, for example, like row 1 of this matrix and convert it back to an equation, remember it was x, y, and then z in that order, this would mean 1x, which you could just call x, 1x, and then plus 0y, so you don't even write the y, and then plus 4z equals 10. So that's just the first row of our result matrix turning into an equation here. But we want to do that with the second row as well. Now notice that's 0, 1, negative 0.5, 3.5, so that would mean 1y, or just y, minus 0.5z equals 3.5. And now we're at the place where there are a couple different ways to write this. Remember, some authors take some different takes on this. Some would say let t be a real number and then substitute the t variable in there. Others would say just use the variables you already have. So it doesn't really matter, but let's go ahead and take a step in that direction. What we'll want to do is solve for y in the second equation and solve for x in the first equation. Now let's see what happens when we do that. If I just pick on the second equation first for a second and solve for y, that would mean I have y equals, I'll add 0.5z to both sides, so I'd have y equals 0.5z plus 3.5, that was already over there. Okay, if I take the first equation and do something similar but solve it for x, then I would have x equals negative 4z by subtracting 4z from both sides, plus 10, that was already over there. And so when we've solved for y and x, notice they're both in terms of z. Okay, so this is where you could have two different options. You could say, let t equal z be a real number, and then you can replace the z's with t's, which would give you y equals 0.5t plus 3.5, and it would give you x equals negative 4t plus 10. So this is a totally valid way of doing it, where you'd write your answer as an ordered triple, but you'd use these t expressions in it. So for x, we'll write negative 4t plus 10, comma. For y, we put what it equals, which is 0.5t plus 3.5. And then for z, remember we said z is t, so we just put t. So this is one valid way of expressing. Remember, this would represent all infinite solutions. It's a formula to do that, where you plug any real number t in to each of these expressions and you get a solution. The other way, though, as we've seen, would be simply to write the ordered triple using or without using the t variable. So go back to where we had solved for y and x and just use those expressions. So x was negative 4z plus 10. We'll put that in the x spot, negative 4z plus 10. In the y spot, we put what that equaled, which was 0.5z plus 3.5. And then for the z spot, we put, well, just the letter z. So we haven't replaced it with t, but you can still see the basically same form of the answer, where z is written in each term's expression. So again, you could use this way or the first way with the t real number trick. It doesn't really make a difference. They both represent the same thing. Let's try a third example where we want to solve the system using Gauss-Jordan elimination on a matrix with a graphing calculator. And this time our our system is given, and we're going to convert that directly to an augmented matrix, as you know by now. Now observe in this system, let me read some of the equations. It's just y minus 5z equals 3, 3x plus 2y equals 12, and 3x plus 10z equals 80. Remember that we have to understand the layout or structure of the system so that we make sure we understand the layout and structure of our augmented matrix. For example, the first equation is missing an x term, the second equation is missing a z term, and the third one is missing a y term. Well, that will affect our augmented matrix, but it doesn't ruin everything for us. We just have to understand that we are going to put all the x coefficients down the first column, and then the y and z's in the second and third columns, but we want to make sure we have everything in the right spot. So we have 0, 3, 3 going down that first column to match the blank x, and then the 3 and 3 coefficients going down. Now it's more typical in a matrix to go across each row first, so I'm going to continue that way. In the first row, I already put the 0 in the first spot, then it would be a 1, and then a negative 5, and then a 3 if we go across each of those. Remember, the second column is going to be our y coefficients, the third column is going to be our z coefficients, the last column is just the constants on the other side of the equations. Across the second row, we already have a 3 there, then we have a 2, 0, and then a 12. Across the last row, the third row, we have a 3, 0, 10, and then 80. And so there's our augmented matrix that we want to take to the graphing calculator for this RREF, reduced row echelon form function on the calculator, which does a whole bunch of work for us. Okay, so I typed our augmented matrix in as matrix A and then performed the RREF feature of the calculator on it. The result is now in the screen. I'm going to scroll through the results because it's actually too big to fit in the simple screen. You have to scroll to the right. The first row reads 1, 0, and then it's 3.333. The 3 is repeating. So we can call that 3 and a third, okay? And then notice though, don't forget the last column there as well. So there's a 0 all the way to the right. You can scroll back and forth to understand what each entry is. Okay, so I've now copied down the result matrix from the RREF, reduced row echelon form feature of the calculator. You'll notice it starts with the 1s kind of on that main diagonal there. But then you'll notice something strange happens in this one. Instead of being all ones on the main diagonal, we end up with a 0, which seems a little interesting. Furthermore, notice this last row. So it's 0, 0, 0, 1. If we were to translate that last row back into an equation, remember the first column's the x's, second y's, third z's. This would mean 0x plus 0y plus 0z equals 1, which is another way of saying 0 equals 1 from this last row, but of course that's not true. So, as we've seen before, when you get a not true scenario like this, we can automatically say that there is no solution, and we would call this inconsistent. And so in other words, you can spot even an inconsistent system while using RREF on the calculator, and this is how. You'll notice the zeros and then the non-zero number it's equal to. So translating back to the equations makes it clear.